Electricity is scary. I'm sure you've seen dozens of warning signs like these, and how plugging a toaster in your bath is a euphemism for suicide. You probably know why this is. Electromagnetism is the only fundamental interaction that is both strong and significant over distance larger than, like, an atomic nucleus. And when I say gravitation is weak, I mean there are not enough words in any language to describe just how weak it is, okay? A sextillion atomic mass units, each about the mass of a proton or neutron, weighs as much as 40 grains of sand or so. On the other hand, a sextillion elementary charges, each the amount of negative charge in an electron, is the amount released by 10 lightning strikes. Other than that, they're pretty similar, actually. Electric charge, like mass, is conserved, so anytime a system loses or gains any, it must be due to an equal and opposite change elsewhere. That reminds me, the other big difference between the two forces is that electric charge is signed. Classical mechanics doesn't prohibit negative mass, but so far we haven't found anything like it, and it would do some pretty weird things if we did. Charges influence the electric potential, which you can think of like a contour map of terrain, because those are basically maps of gravitational potential. This gives rise to the electric field, which is basically how much and where the test charge would accelerate if the potential actually was a bunch of mountains and valleys and stuff. Now, as you know, interaction between objects with mass and the gravitational potential field creates gravitational potential energy, and interaction with the gravity field creates the gravity force, and so on. Electricity behaves much the same way. No, we'll talk about you some other time. Alright, enough of this wishy-washy math. It's time to get into the good shit. First, we need to talk about electric batteries. I prefer electric assaults. Now, these things, as you can tell by this one's idleness, do not produce energy. Rather, they induce a potential difference between the ends, the cathode and the anode. 200 years ago, this is some pretty advanced shit, but gravitational batteries have been around since, like, the dawn of history, so I'm not really impressed. What's cool about batteries is that they lead to a flow or current of charged particles through whatever path takes them to the negative side. Positive side? Whatever, nobody likes physicists anyway. This path is called a circuit. It has to be complete or else there's nothing to create a current. Now, just like people, wires are not perfect. The materials inside the wire tend to obstruct the current to varying degrees, called resistance. In metals, this is proportional to the potential difference. In other conductors, not really. The resistance in the wire is inversely proportional to its area and proportional to its length and the material-dependent resistivity. Resistance creates a drop in electric potential difference, much like how friction reduces the efficiency of a slide. Most wires don't create that much resistance, but I mean, I'm sure you can guess what a resistor does. Also, capacitors. These guys store electric charge in a circuit, and their capacitance tells you how good they are at it. The kind depicted in the diagrams and stuff is called a parallel plate capacitor, where two strips of conductor polarize the electrons into a positive and negative side. The effectivity of the capacitor is proportional to the area of the plates and inversely proportional to the distance between them. These can be outfitted with a dielectric between the plates, which increases the permittivity constant, and thus the capacitance. Usually it's written relative to the permittivity of a vacuum. In a live circuit, the rate that the capacitor discharges is proportional to the amount of charge already accumulated in it, which, as you know, creates an exponential curve for the voltage over time. The same goes for charging the capacitor, so introducing a switch allows you to alternate quick charges and discharges, which is useful in, like, a camera flash or a heartbeat. For more complicated circuits with junctions and stuff, Kirchhoff's circuits laws are useful for pinpointing the current and voltage of certain segments, given that you're in the physics world and not reality. Now, for the capacitor here to become charged, the electrons in this battery have to move over here somehow, which means that the electric force must do work. Plugging in the potential energy formula we know from earlier yields the equation for electric potential energy stored in the capacitor. And this is why electric current is so useful. Doing consistent work with it is extremely straightforward. I mean, there's a reason that power, in all of its many forms, has become almost synonymous with it. This all raises an obvious follow-up, though. What does gravitational current do? You get a shitty approximation by stealing the vector calculus relation between electricity and magnetism, but if you want an actual explanation, well, who fucking cares anyway?